Hi everyone, myself Dr. Lakshmi Prasad, working as a professor in the Department of Computer Science in Institute of Aeronautical Engineering, Hyderabad. In this video, I'm going to discuss about EULERS and Hamiltonian paths of the graph. So before going to see that, so we are going to discuss about 7 bridges of cosine bridge problem. So which should be arised in Germany. So the descendants of this cosine bridge problem uh, is that so the German people wondered if it was possible to take a walk a tour of time of town and then cross each other of 7 bridges over the Persel River exactly once. And is it possible to start at some node and then take a walk that uses this each edge exactly once and ends at this starting node? So here in this cosine bricks problem, so the people are going to be wondered having a tour of town such that we're going to be cross the several bridges over the Persel River exactly once. So the problem is that, so is it possible to start at some node and then take a walk and then uses the edge exactly once and then ends at the starting node? So for that, how this problem is going to solve here is that, so this problem is going to be solved in the form of a graph, where we can able to redraw this original picture as long as every edge between the nodes I and j in the original. So for that, this is the representation of that one. So later on, this one is able to redrawn it, and then we should be able to show it in the form of graph exactly how it looks like. And this one, what we called as a vertices of the graph, and this uh, paths what we called as the edges they're going to consider it. And so this is the Euler's um, Euclidean, so which has no tool that uses exactly once, and even if you walk to start and finish at different places, so can you see how it one? So that for that, the what is the definition of this Euler's definition? So Euclidean path or other synonym what we called as Euclidean tail or Euler walk. So in the graph is the path that uses each edge precisely once. If such a path exists, then the graph is traversable. And Euclidean cycle or Euclidean circuit or what we call as Euler tool in the graph is a cycle that uses exactly each edge exactly or precisely one. If such cycle exists, then the graph what we call it as Euler's or Euclidean cycle. So normally that terminologies will be Euclidean path. So for this, the other synonym what we called as Euclidean trail or Euler's walk in a graph. And that means in this graph, using the edge exactly once such that the paths will what we called as Euclidean path. And uh, if such path exists, then the graph what we call it as the traversable. Similarly, the other synonym is that Euclidean cycle. So for that, what we called as Euclidean circuit or Euler tour uh, in a graph. So which is a cycle that uses the each edge exactly once. And if such cycle exists, then the graph what we called as Euclidean cycle. Suppose a graph is going to have vertices like this. So what is the path that exists in between them? So AB, B, D, and then DA and DC and CD. Okay, like this we are going to be find the Euclidean path here. So for this, in this one, how I'm going to present it is that AC to AC and then CD, and then DE, and then EB, BD, DA, and A to B. So like this, we can able to establish the path of Euler's. So some of the cases I can able to show that this is not an Euclidean. So in fact, it contains no Euler trail. And for the Euler theorems is going to be suggested here. So the connected graph is said to be Euclidean if and only if G is connected and has no vertices, of odd degree, and the connected graph has an Euler trail from a node A to some other node B if and only if the graph is connected and A not equal to B are the only two nodes of that order. So the connected graph is going to have an Euler trail from node A to some other node B if and only if the graph is said to be connected and A not equal to B are the only two nodes. And Euler's theorem, so assume that the graph is going to have Euler trail from node A to node B and A and B not necessarily distinct one. So for every node besides this A and B, so this T uses an edge to exit for each and other edge it uses to enter. So then the degree of the node is going to be given by, so if A equal to B, then A also have even degree, and if A not equal to B and A and B both have odd degree. So this one what we called as Euler circuit, and odd degree what we're going to have is that Euler path. Okay, so if A and B are equal, then also then A is going to have even degree, that what we call as Euler circuit. If A not equal to B, then A and B both have odd degree, then it's what we call as Euler path. Assume that this graph is going to have Euler trail from A to B, and for every node besides A and B, the Euler trail uses an edge to exit from each other, and it uses to enter actually. And another thing is that a connected graph is said to be Euclidean if and only if the G is connected and has no vertices of odd degree. Suppose I'm going to build the path like this, A to B, and then B to C, C to F, and then F to A. So this one what we called as Euler circuit constructed if all the edges are going to be used. Is it true here or not? So for this one, similarly, delete the path, simple path. So what I said is that, so A, B, B, C, C, F, and F, A, and is the C is the common for the expected common subgraph with its parent, and so construct a subgraph that may not be connected, and C is the common vertex of the subgraph with its parent, and C has the even degree. So start at C and then take a walk. So I'm going to like this. So C to D, C to D, D to E, and then E to C. So splice the circuits in the two graphs. So what is that is, so AB, BC, CF, and FA is one of the circuit, and if I'm going to join that CD, DE, and EF with another circuit. So formally I'm going to get AB, BC, CD, and then DE, EF. So if I'm going to match both the circuits, then it should be considered as a Euler circuit here. So this is the one of the theorem of that. And Euler circuit is going to be defined as the circuit C. So a circuit of G beginning at the arbitrary vertex, and then add the edges successively to form the path that returns to this vertex. And so here, and this one should be obtained from G minus of above circuit. Similarly, while H is going to have the edges, so Subcircuit SC is going to be like a circuit that begins with vertex in H and also in vertex in C, and H minus of that SC should be of all isolated vertices, and the circuit is going to have Euler circuit. So how we are going to this represent this graph in the form of incidence matrix. So for this, normally this incidence matrix is going to be shown along the vertices and then edges. So in rows, I'm going to consider the vertices here, vertices of the graph, and this one, the columns, I'm going to consider uh, edges here. So that's what I'm going to take. So A, B, C, D, E, F. These are the vertices of the graph, and these are the edges that are considered here. So for this, what I'm going to say that is, uh, suppose if I'm going to have an edge like this, so A to B. So for A, what are the edges that I'm having? So 1, and then E. So E is going to have incident on this, so it should be -1. Similarly for B, so for B, E1 is incoming and E2 is outgoing, that's why it should be -1 and then 1. And for C, it should be E3 should be leaving, E2 is coming, and E5 also incoming edge, and E6 is leaving. And similarly for D, E3 it should be incoming, D4 leaving, and E4 means that for E, so it's both one is incoming and another is leaving. And for F it should be E7 leaving and E6 incoming. So like this I'm going to represent this incidence matrix of the directed graph. And next we are going to see about Hamiltonian graph. So what is this Hamiltonian graph? So the graph which is going to have Hamiltonian path, that's graph what we called as an Hamiltonian graph. So normally this Hamiltonian path is the traceable path, so that visits each vertex exactly once. And the cycle, so the graph which is going to have a Hamiltonian cycle is called as Hamiltonian circuit, vertex 2 of graph cycle. So which is going to be visits each vertex exactly once, except for starting, and then which is visited at the start and then once at the beginning. So the graph which is going to having this Hamiltonian path is called traceable graph, and the graph which is going to have this Hamiltonian cycle is said to be Hamiltonian graph. So any Hamiltonian cycle can be converted into Hamiltonian path by removing one of its edges, but a Hamiltonian path can be extended to the Hamiltonian cycle. So if its endpoints are said to be adjacent here. So the graph of vertices of a dequadron, so is it a Hamiltonian or not? So that's why I have to solve this. So is this one as a Hamiltonian? Yes. Is this one should be the Hamiltonian graph. So normally this graph is going to have one Hamiltonian path but not Hamiltonian tour. So that is the thing we have to remember in Hamiltonian graph. So similarly this one, so this one has a Euler tool but no Hamiltonian path here. Okay, so in this graph we can able to obtain the Euler tool, but Hamiltonian path is not there in this graph. Similarly, this some notations may be defined for the directed graph, where the edges of the path or cycle required to point in same direction, so that is connected tail to head. Hamiltonian cycle problem or Hamiltonian circuit problem in the graph theory is to find Hamiltonian cycle in the given graph. So that is the major problem. So how are we going to identify this Hamiltonian cycle problem? So by able to identifying this Hamiltonian cycle. Normally, this Hamiltonian paths problems is to find a Hamiltonian path in the given graph. So there is no simple relationship between the two problems, and this Hamiltonian path of the graph is equivalent to the Hamiltonian cycle problem. And next one, so both the problems will be NP complete. So however, there will be a certain cases of the graph always contain Hamiltonian paths. Suppose for example, so it is known that every tournament has an odd degree of the Hamiltonian paths. So Hamiltonian graph, so where the notation should be deferred in the directed edges, and where the edges of the path are cycle required to point in some directions, and the graph which is going to have Hamiltonian cycle is called Hamiltonian uh, path problem, and the graph which is going to have Hamiltonian circuit is said to be Hamiltonian path. So in this Hamiltonian graph, we are going to see about two types of arcs. The first one is that a graph is a simple one with n vertices, where n should be number greater than 2, such that the degree of every vertex in the graph is having at least 6 by 2. So there should be here two types of theorems are going to be suggested here. So first one is the Dirac's theorem. So if the G is the simple graph with n vertices, then with n greater than or equal to 3, such that the degree of every vertex in the graph should be having at least n by 2, and then the graph has Hamiltonian circuit. If similarly, if the graph G is simple with n vertices with n greater than or equal to 3, such that the degree of U plus degree of V should be greater than n for every pair of non-adjacent vertices. So then G has this Hamiltonian circuit. So here what I'm going to say that is here a graph, simple graph with n vertices is going to be have n greater than or equal to 3, such that the degree of V plus degree of V should be greater than n for every pair of non-adjacent vertices U and V in the graph, and the graph should have Hamiltonian circuit. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.